Hey, good morning, everybody. This is Mr. Aynesworth at Great Oak High School here in Temecula, California, and we're in financial algebra, and we're in Chapter 9, Section 9, and we're working on these linear programming problems, how to optimize a problem and find the optimal or best solution, okay? And we're at number 10 here, so notice that I reformatted the number 10 on the left. I've got the actual workbook problem on the right. And then also you need your Desmos here. We'll validate everything at the end using Desmos graphing program. All right, but we're going to do everything all by hand. First, get out your red pens and highlighters because we're going to annotate the problem, because the most important part is how to interpret the problem, organize it well, and write the system of constraints so you can actually optimize it. That's the hardest part. So we're going to go slow here, dissect it, annotate it, take it piece by piece, and try to write the system of constraints, which is called modeling the problem. And then after that, it's pretty much easy. All right, so I'm going to zoom in here and let's get started. All right, so this is a bakery problem. This is kind of fun. All right, Raul and Carla own the Cakery Bakery. I always try to make fun with the names there. They make specialty cakes for all occasions. Cool. All right, they have just been hired to provide the desserts for a large convention that will be held in 1 week. They will need to hire bakers and cake decorators. Okay, well, that makes sense, right? If you're making cakes, then you need bakers and you need the decorators. All right, bakers make $600 per week. Okay, so right away, notice that I have a table here so that we can organize our information. I've got the first row for the baker, second row for the decorator, and then if there are any constraints, we can also organize them in there. So first thing I see right here, the first piece of information that I see are the rates, okay? Bakers make $600 per week. Well, guess what? That's a rate, right? And that's for the baker. And then let me read on here. It says the cake decorator, they make $900 a week. It takes more skill to decorate, I guess. And because of that, they make more money. All right, so what we want to do is we want to organize our information here. So $600 per week for the baker, $900 per week, all right, for the decorator. So that's the first thing we know. All right. The company knows that they will need at least, look at this. Whenever you see words like this, at least 3 bakers and at least 5 cake decorators, that right there is some constraints. All right, we need to work on that. So what we're going to do is we're going to take a look at the workbook too, side by side, and just kind of see what's going on here. Because they step it out over here on the right, or in your workbook here, and they kind of give you some suggestions, which is not too realistic. Normally when you solve a problem, you don't have all these step-by-step stuff. You don't even have a table. You got to learn how to organize and on your own. You have to learn how to interpret the words here. But we're going to use the workbook to help us out. So it says, let X represent the number of bakers and needed, Y represent the number of decorators needed. Okay, well, that makes sense, because if you read on the problem here, it says a baker spends 4 hours designing and 15 hours creating the cakes. A cake decorator spends 8 hours designing and 15 hours creating the cakes. Raul and Carla know that they will need at least 80 hours of design and 180 hours of creation. How many bakers and decorators will be needed for the job in order to keep costs at a minimum? So our goal here in this problem is to minimize costs. In every business, you want to maximize the profit and you want to minimize the costs. In this case right here, our goal is to minimize costs. That's going to be our objective. So let's write that down here at the bottom here. We want to minimize. This is our goal now. Okay, objective is goal. We want to minimize the cost, so we need to write a cost function. Here, we'll do that here in a minute. Okay, that's the goal. All right, so we've got to define our variables. X represents the number of bakers, Y represents the number of decorators. All right, so always define your unknowns. X represents the number of bakers, okay? Because we don't know. It says how many bakers and how many decorators do you need. Whatever you don't know, that is your variable. Okay, number of bakers needed. Y equals a number of cake decorators. Decorators for short, okay? There we go. So now we know what we're trying to find. Now we have to interpret everything. All right, so And then it says here in part A in the workbook here, it says write the cost objective function. Well, let's read that again and let's figure that out. The cost objective function. All right. Well, it costs money because for the bakery, because you have to pay your employees. You got to pay the baker $600 per week, and you got to pay your decorators $900 per week. And so obviously there's a cost associated right there. So let's understand that there's going to be X bakers and there's going to be Y decorators. And notice that for every baker, you have to pay them $600 per week. And for every decorator, you have to pay them $900 per week. So if you have one baker, then it's $600 per week. If you have two bakers, it's 2 times $600. If you have 3 bakers, it's 3 times $600, and so on. So what you need to do is you need to take the rate and multiply it by the number of bakers that you employ, and then you take your rate for your decorator, which is $900 per week. All right, and well, guess what? You multiply that by the number of decorators, and that will be the total cost. So when you take a look at that, the cost is going to be your rate, which is $600 per week. All right, for the bakers, multiplied by how many you have, plus the 900 times however many decorators you have or you employ. That you employ, and that is if you add those two up, you get the total cost. Okay, in respect to your employees, because it takes some expenses to run the business. All right, you need employees. You need X bakers, Y decorators, and each one has a rate associated with because they earn money too, right? Okay, so that's part A. Part B, write a constraint inequality for the number of bakers needed on the job. Well, you got to read the problem and get organized. So if you read the problem again, it says the company knows that they will need at least 3 bakers. Okay, and at least 5 cake decorators. Okay, so we need to write that as a constraint. Okay, so let's just do that down here. So down here. All right, at least 3 bakers. Okay, so whatever X is, X stands for the number of bakers. All right, you need at least 3. All right, at least means greater than or equal to. And at least 5 cake decorators will mean that's greater than or equal to 5. So X, which represents the number of bakers, has to be greater than or equal to 3. This is a baker constraint. So for the bakers, let me redo this here. So number 1 refers to the bakers. So this is the constraint on bakers. X has to be greater than or equal to 3 here because it says you need at least 3 bakers, and you need at least 5 cake decorators. Okay, so there's a decorator constraint, and that means Y has to be greater than or equal to 5. Okay, so that's our second constraint because it says you need at least 5 cake decorators. All right, and that right there, my friends, is what the workbook is talking about right here. It says, write a constraint inequality for the number of bakers. Well, remember, bakers is X, decorators is Y, and if you're employing X bakers and you need at least 3 of them, that's got to be greater than 3. And if Y stands for the number of decorators, well, and you need at least 5 of them, well, then that means Y is greater than or equal to 5. Okay, so what the workbook is trying to do is trying to step it out, help you step it out and get some constraints going. Okay. All right, going back to the problem here. It says baker spends 4 hours designing. Okay, so there's 4 hours design hours here. Each baker takes 4 hours of designing and 15 hours creating. So 15 hours of creating. So now what I'm doing is I'm interpreting the problem here. So the baker spends 4 hours designing and 15 hours creating. Okay, that's here. Okay. Now this is a cake decorator spends 8 hours designing and 15 hours creating. Okay, well let's fill that out. Okay, so a cake decorator spends 8 hours. This is designing. Okay, designing is the second column, and then 15 hours creating. So their time requirements are a little bit different. Okay, the same in the creation, but different in the design. All right, because decorating, I guess, takes twice as long, and because it's more complicated, right? So Raul and Carla know that they will need at least, look at this, at least 80 hours of design. Okay, again, greater than or equal to 80. and 180 hours of creation. That's at least. That means greater than or equal to. So for the last row here, I said, are there any constraints? And well, there is. I said they need at least 8 hours of design. Okay, so design at least 80 hours, so greater than or equal to 80. So this is greater than or equal to 80 hours total. All right. And then here, creation, well, guess what? That's got to be greater than or equal to 180 hours. That's a minimum, okay? So these are minimums. And then how many bakers and decorators do we need for the job to keep the cost at the minimum? All right, so how do we interpret this? Okay, so here we go. We need some constraints. So the workbook is going to give you a suggestion here. It says use your table to write the constraint inequality for the design hours needed to complete the job. The design hours. Okay, so let's do that. So let's focus in here. So our next constraint, our design hour constraint. So number 3 here is the design hour constraint. And what we're going to do here is that we have to understand that for every baker it takes 4 hours. So if you have 1 baker, it's 4 hours, 2 bakers, 8 hours, 3 bakers, 3 times 4 is 12 hours, and so on. For the decorator, okay, if you have 1 decorator, it takes him or her 8 hours. If you have 2 decorators, 2 times 8 is 16 hours. If you have 3 decorators, it's 3 times 8 or 24 hours. But in essence right here, what you have to do is you have to take the time required and you multiply it, okay? You multiply it by the time required by the number of people that you need in that position right here. And whatever that total is, it's got to be greater than or equal to 80. So 4 hours times the number of bakers plus 8 hours times the number of decorators has got to be greater than or equal to 80. So you're going to take this information here and you're going to write an inequality. 4 times x here, 4 times x plus 8 times y, it's got to be greater than or equal to 80. And this is your design hours. Okay. So for every baker, it takes 4 hours. So you take the number of bakers, multiply it by the hours to get the total time for the bakers. You do the same thing for the decorators. You take the time times the number of decorators, you get the total time for the decorators, add them up. So that's 4x plus 8y. That'll give you your total time, and that's got to be greater than or equal to 80. Now we're going to do some, we have a constraint on the creation hours too. So with that in mind, so we're going to take this information here and we've got to write a constraint on that. So design or a constraint on the creation hours. Okay, so here we go, same logic. For each baker, it takes 15 hours of creation time. So for 1 baker, it takes 15 hours, 2 bakers, 2 times 15, 3 bakers, 3 times 15, 4 bakers, 4 times 15. So in general, you take your time, multiply it by the number of bakers, which is 15 times x. And then for the decorator, well, they require the same amount of creation time. So 15 hours times the number of bakers, or decorators. So we're going to take 15 times x plus 15 times y, and that's got to be greater than or equal to 180. So 15 times x plus 15 times y, and that's got to be greater than or equal to 180. And that, my friends, is called the creation constraint. So you have a design constraint, creation constraint, and you also have a couple initial constraints on the number of bakers and decorators. Because in the problem, if you go back and read it again, it says in the beginning they will need, okay, the company knows that they will need at least 3 bakers and 5 cake decorators. At least, all right, they run the business. So they need a minimum number of people. All right, so these are minimums. Okay. So now we have the 4 constraints. We don't need to worry about the non-negative constraints here, because if x is greater than or equal to 3 already, then obviously it's positive, and if y is greater than or equal to 5 already, then obviously it's positive. So the non-negative constraints are not needed because they're already positive in the first 2 constraints. So now all we need to do is graph the system of constraints, find the feasible region, find the corner points, and then optimize the problem. And remember, we're trying to minimize the cost here because we're dealing with the cost in this problem here, because we know that to employ the bakers and decorators is obviously going to cost the company a lot of money, because each baker makes 600 per week, and each cake decorator makes 900 per week. All right, and we want to minimize that because we want to maximize profit. Okay, so you always minimize costs, and you always, in order to maximize profit in the long run. All right, so let's take these right here, and let's work with these constraints. And here we go. So let's go to the next page here, where the graph is right here, and let's take these guys and let's graph them. All right, so here we go. So x greater than or equal to 3. And by the way, we don't need Desmos here. Okay, notice that I'm not using it right now. I will use it afterwards just to confirm everything. All right, but I'm working through all these problems with you guys without Desmos to show you that we can solve all these without without a graphing program, okay, like Desmos. Of course, it makes it easier, but we can do it without it initially. All right, so the first constraint, x greater than or equal to 3. So what you need to do is find 3. And notice that the scale here from 0 to 2.5, there's 5 grid lines between 0 and 2.5. So 2.5 divided by 5 is 0.5. So that's why I said the scale is 0.5 or 1/2. So keep that in mind. So let's color code these graphs or inequalities. So the first one, x greater than or equal to 3, you got to find 3. So find 3. So here's 1, right, and there's 2, 2.5, and there's 3. All right, so be careful there. The scale is 1/2. So we find, let's graph it as a vertical line here. You know what? Let me just do this. Okay. Let's see if I can adjust that a little bit. Yeah, that's not that's not a vertical line here. So let me adjust that a little bit. There we go. That's much better. All right. When you're greater than or equal to 3, everybody, you are to the right of 3. I mean, 3, 4, 5. Bigger numbers lie to the right. So x greater than or equal to 3 is obviously to the right of 3, right? Like 4, 5, 6, 7, and so on. Look at all the x values to the right. All right. Now, so that's the first one. Second one, y has got to be greater than or equal to 5. Okay. Now, if you're greater than or equal to 5, then you're above 5. So that's going to be a horizontal line. Okay. So let's graph that right there. And obviously, y values that are bigger than 5 are above it. Okay, use your common sense. All right, if you're greater than or equal to 5, you're above 5, like 6, 7, and 8. Okay. All right, next inequality here. We have 4x plus 8y is greater than or equal to 80. So let's take it over here. Let's get it in slope-intercept form like we always do. Not that you have to do that. You could use intercepts here. If you want to use intercepts, let x equal 0 and find y, and let y equal 0, find x, and graph it that way. That's an awesome method. I use that all the time. In fact, I'll show that here in a minute. Okay, so, but if you want to isolate y and get in slope-intercept form, let's do it. Subtract 4x, and you get 8y is greater than or equal to negative 4x plus 80 divided by 8. Everything. So y is greater than or equal to negative 1/2 x plus 10. So the slope is negative 1/2. The y-intercept is obviously 10. So we're going to start at 10 and then go down 1 right 2. Okay, so let's start at 10. And let's see, so here we go. So there we go. Let's start there through y-intercept. And now, if I'm going to multiply this by 10 tenths, so I'm going to go down 10, right 20. All right, just to make it easy. So I'm starting at 10, so I'm going to go down 10, right 20. Ooh, right there. Okay, look how easy that was. Okay, we talk about doing that in class all the time. In the past few days when we've been working on these problems, you can adjust your slope and make it look like anything you want. So let me adjust this line a little bit. You want to be really accurate on your line because we're trying to find intersection points after this. We've got to find the corner points. And if your line is not drawn correctly, then you're not going to find your corner points correctly. All right, now this inequality right here is it's greater than or equal to. So this We shade here, we shade up. The solutions are above the line. Okay, so let's go above the line here. So this inequality describes y is greater than or equal to negative 1/2 x plus 10. All right, almost done. Next one. So on this one here, let's do some. So let's put it. I got to pick a different color. Okay, purple. Okay, so here we go. So the fourth one. So I'm going to take 15x plus 15y is greater than or equal to 180. I'm going to divide everything by 15. Well, you know what? I'm going to subtract 15x here first. I'm going to get it in slope-intercept form. So I have 15y is greater than or equal to negative 15x plus 180. Divide everything by 15. And y is greater than or equal to negative x. All right, plus what? Maybe 12. Okay, so let me see. Sorry, 15 times 12. 10, yeah, that's right. Okay, so now the slope is negative 1. All right, y-intercept is 12. So now we start at 12. So I got to find 12 on the y-axis right here, and we'll do this in purple. So let me zoom in here. I got to find 12. And 12. Let me put this one. I'm going to do this one. I should have done this in red. Let me see. Let's just change this. We're going to do this one in red. Okay, so this one's in red. So right here, so we can see it. So here I'm going to start at 12. Remember, this is a y-intercept now, and the scale is 1/2. So obviously go below 12.5 at 12, and the slope's negative 1. So I could go down 12 and write 12. That'd be a slick way to do it. So negative 1 is the same thing as negative 12 divided by 12. So I go down 12, write 12. So down 12, write 12. Should be right here. Okay. And again, we'll check everything later. So let me grab my line tool. You guys draw your line. Be accurate here, because, like I said, if you're not accurate with your boundary lines, then finding the intersection points is going to be difficult. Okay. Okay. So now let me see. This is greater than or equal to, so we shade up. All right, the solutions are above the boundary line. So y is greater than or equal to negative x plus 12. And now we have to find the intersection of all the regions. All right, so we got to be above the green line, above the black line, above the red line, and to the right of the blue line. Well, they all intersect out through here. Okay, so let's shade in the feasible region here, which is your first experience of an unbounded feasible region. And that typically happens in minimization problems. See, we're trying to minimize cost. Okay, the cost, there's no limit to cost. I mean, the more bakers and decorators you have, the more it costs, right? And there's no limit to the size of a company, theoretically. All right, and that's why this doesn't have a bounded area. Okay, it's not bounded like the previous ones. Okay, so what we want to do is still find the corner points, though, so which we call vertices. So let's label them here. Okay, so here we go. So we have one here. Let's call this one V1. All right, we have one here. You know what? Let me. Probably should do this in black, maybe. Right here, V1, V2, and then here, V3, and that's it. So we have 3 vertices, only 3. All right, there are no other vertices. And so let me see. We'll check this with Desmos, but I'm thinking here that this is at 3, so 3 comma looks like 3 comma 9. Okay, 3 comma 9. So V1 is at 3 comma 9. I'll verify that later. V2, it looks like if that's 5, this is 4. So up 4, right, and then go left, right, that looks like 8. So this looks like at 4 comma 8. The V3, go down, that's 10, and then 5, so 10 comma 5. So 10 comma 5. All right, so you know what I'm going to do is I'm going to, before I maximize or minimize this, I'm going to check everything with Desmos here. So let's do it. Get ready. Do this with me here too. All right, I'm going to just type in the inequalities and then adjust the scale. So here we go. Let's type them in. Easy as pie. Okay, or easy as cake. Ha. Okay, so x greater than or equal to 3, y greater than or equal to 5. Anybody can do this. All right, 4x plus 8y is greater than or equal to 80. All right, and then 15x plus 15y is got to be greater than or equal to 180. All right, well, let's expand this here and let's adjust the scale. Oh my God, it looks the same. Okay, so let's go ahead and click on some intersection points here, just so we can compare. Okay. I'm clicking on all the intersection points here, but just because I wanted to show you that the graph that we created is the same. Okay, so this darkest region to the upper right is the feasible region. So let's go ahead and bring this in. All right. Let's compare. Okay. So now we have what's produced by Desmos here, and notice that the vertices are the same. So V1 is here, V2 is here, V3 is here, and they all match what I came up with earlier. Okay, so that's good, and this is your feasible region out here. Feasible region, this region here. All right, what's the fancy name for solution region? Okay, so we have our vertices, 3, 9, 4, 8, 10, 5. What we're going to do is we're going to use those to optimize the problem. So let's go back to the problem and remember what we're trying to do. Now remember, in business, you want to maximize profit, and at the same time, you want to minimize cost. And it says right here, how many bakers and decorators will be needed to keep the cost at a minimum. That is your goal. Okay, so your goal is to minimize costs, minimize cost, and because of that you have a cost function, $600 times the number of bakers plus $900 times the number of decorators. This is money, okay? And our vertices, V1, oh, I forgot what they were. Okay, so we gotta look. Okay, so V1 was 3, 9, then 4, 8. So 3, 9, V2, 4, 8, V3, 10, 5. So 10, 5, and then you just substitute them in, and you get a cost for each. Substitute in, get a cost, substitute in, get a cost. And at this point, you know, I use Desmos. I mean, I showed you guys how to do it very easily in Desmos, so let's do it again. All right. Let's put it side by side. And let's get a cost. So we set up a table. We put the points in. So put in the points, 3, 9, 4, 8, 10, 5. And then put in your cost function, 600. All right, times x1 plus and then 900 times y1. And it calculates everything for you. So notice it gives you the cost right here. So let's write them down. So we have 9, looks like 9,900. Second cost would be 9,600. Third cost would be 10,500. All right, and then if you compare everything, you'll notice that we have a minimum, all right, at 4,8. So this is the minimum cost. All right, and it occurs, okay, this occurs at this point right here. So this becomes the optimal solution, okay? So you have to understand that x is 4, y is 8. But again, what do they mean? So you go up here to your definitions right here. All right, and it says that x is the number of bakers, and so we need 4 bakers, and then we need 8 decorators to keep the cost at a minimum of $9,600. And that, my friends, is what you write down. So company, all right, should hire, okay, looks like 4 bakers, 4 bakers and 8 decorators. All right, to keep the cost minimized. So to keep the cost minimized. All right, so minimum cost would be up there. It says 9,600. Okay. And that's what you would tell. So if you were the person in the company making all the decisions, you would tell the CEO, and after you do all your mathematics and analysis right here, based upon the constraints of the problem, all right, you would say, hey, CEO, whoever that may be, you should hire 4 bakers and 8 decorators because that's going to minimize the cost to maximize the profit, okay? And there we go. And all the steps here in your workbook here is what we did over here on the left. Okay. More importantly, here, guys, the skill that you guys have to focus on here is how to interpret this problem and organize the information effectively so that you can actually translate it into what are called constraints, which are inequalities. Okay. And then, of course, you use the ideas of linear programming to optimize the problem. And optimize means find the best solution. And in this case, it means to minimize the costs. Okay? All right. Well, this is Mr. Aynesworth. I will see you in another lesson again later on. Take care and study well. All right. Bye-bye.